Very good morning. So I'm Ramasuri Narayanam from IBM Research. So before we get started into the topic, right? So cooperative games and solution concepts. So I'll give a quick introduction about myself. So I received my PhD from Indian Institute of Science, IISc, in 2011. The area of topic in which I worked is social media analytics using game theoretic models. And after I graduated, I joined IBM Research. Since 2011, I am with the same organization. So at IBM Research, so I work on largely in the areas of like social media analytics, business analytics, and more recently, I am working in the areas of multi-agent systems, decision making, right, evolution of cooperation on networks, these kind of topics. And of course, being in industry, so we should participate in projects wherein like data science related skills are required, machine learning, data mining type of skills are of course required, right? So we do work in those areas also. One of my, other topics of interest being like graph representation learning. So recently I'm also exploring a lot in the area of graph representation learning. Okay, so with that brief background, let me get started. So cooperative games and solution concepts. So this is like a basic talk which introduces several, foundational topics in the area of like cooperative games and associated solution concepts. Okay, so this is the agenda for my talk. So I'll quickly give an introduction to cooperative games, and then we will get into the topic of correlated strategies and equilibrium. Then another notion called Nash Bargaining solution, followed by transferable utilities, and a couple of foundational solution concepts in cooperative games, namely core and Shapley value. Okay, this is the agenda for the talk. So let's get started. So in the previous talk, so my colleague, so Dr. Dinesh talked about non-cooperative games, and you would have understood what it means and the foundational concepts like Nash equilibrium and so on and so forth. So I will continue from there actually, right? So consider this standard 2x2 matrix game, wherein there are like two players and every player has two strategies. Namely, so for first player x1, y1, for the second player the strategies are x2, y2, and this is the matrix. So based on the kind of things you understood, so what is the Nash equilibrium of this game? Can anybody try to take an attempt? So does Nash equilibrium exist first of all? If so, what is the Nash equilibrium outcome? One comma one, absolutely. So this is being like a matrix game, you can easily verify. So one is greater than 0 and this one is greater than 0. Otherwise, you follow that equation. Either way, you should be able to get the solution. So y1, y2 is the equilibrium outcome, wherein the payoff to the players is 1 comma 1. But by looking at the matrix here with the 4 cells representing the payoffs to the players, do you think 1 comma 1 is the optimal payoff that the players can get? No. So the optimal in the sense the maximum, I would say. So the maximum payoff that players ideally can get is this outcome, x1, x2, wherein both players get a payoff of 2 each, right? But unfortunately, 2 comma 2 is not a Nash equilibrium, right? Because this 2 is less than 6 and this 2 is also less than 6. It's not a Nash equilibrium. So because of that reason, so players voluntarily cannot select these two strategies, x1 and x2, whereas y1 and y2, being a Nash equilibrium, there is no need of any central authority or any binding agreement for, among the players to execute that strategy. So Nash equilibrium outcomes, to implement Nash equilibrium outcomes, we don't need any contracts or the presence of any central authority who can prescribe the strategies. Whereas when it comes to these kind of non-equilibrium profiles, right? So in order to attain this kind of they are like socially efficient because both players will get a payoff of 2 comma 2. So this 2 is greater than 1 and the second payoff the player 2 gets 2, this 2 is also greater than 1. But unfortunately, it is not Nash equilibrium, players they don't believe among themselves and execute this profile x1 comma x2. So on the other hand, if players are like cooperative to each other, right, then this may be possible. So now going forward, we try to understand some solution concepts using which we will go towards this direction actually, from 1 comma 1 outcome to 2 comma 2 outcome. So being cooperative, people can achieve this kind of socially efficient outcomes. So that is the motivation behind my talk, okay? So that's what is clearly mentioned. So players can achieve higher payoff by cooperating. Okay, so towards this direction, the first step is called correlated strategies. So what is a correlated strategy? So let's consider a correlation of the players C. C is a subset of N, okay? So a correlated strategy for a given subset of the players C is nothing but it's a probability distribution over this set capital SC, which is nothing but the cross product of the players' strategies in the set C. Okay, so SI is the set of strategies of ith player, and you consider all such strategy sets of all the players in that correlation C. Take Cartesian product of it, you get all possible profiles of strategies for the players in the set C, whatever SC. So now look at probability distributions over SC. So you would have seen this delta of SC means the probability distributions, right? So now tau C is called a correlated strategy for a correlation C. Clear? Okay. So now we define something called a contract. So it's just extension to what we have defined like correlated strategy for a given correlation. So if there are like n players, there are like 2 to the power of n possible subsets, right? So for every subset, you can define this correlated strategy, right? So now you write down the correlated strategies of all possible subsets as a profile, as a vector, is called a contract. So a contract is a vector, tau, correlated strategies of all the correlations, right? So for a fixed correlation C, this you have seen, this is nothing but the correlated strategy associated with the correlation C, and you take cross product over all possible subsets C. Okay, this is called contract. So contract defines an extended game called contract signing game. That is the notation. So now you understood what is a correlated strategy, right? So now you think of some mediator. So who can consider any profile from this correlated strategy belonging to a correlation C. So, consider a particular correlated strategy associated with a correlation C. It's called tau C, belonging to this all possible probability distributions over SC. Right? Now it's being a probability distribution. Following that, mediator can randomly pick one particular pure strategy profile. You understood, right? Probability distribution over all possible profiles of pure strategies, right? So suppose a mediator selects a particular pure strategy profile randomly, relation C, and then prescribes that, okay, so all the players in the subset C should play this pure strategy profile. He prescribes, okay? But players are like playing the game independently. So what is the hard and fast, why should players follow the prescription given by the mediator, right? So as a mediator, he went ahead and prescribed a particular pure strategy following the correlated strategy, right? But it is up to the players whether they execute that strategy or not. They need not, right? Provided that pure strategy payoff is not beneficial to them according to their utility function. So that's what we will see. So under what conditions, right? Okay. Where is that? This one. This is a Cartesian product. Yeah, product of all SIs. Yeah. It's a pure strategy profiles. I mean, the set of all pure strategy profiles. This one. Of the players belonging to the coalition C. Okay. So now we are going to look at the conditions under which the prescription given by the mediator would be indeed executed by the players, right? So in general, they don't need, because the utility perceived by the agents as prescribed by the strategies from the mediator need not be beneficial for the players, in which case players don't need to play those prescribed strategies. So under what conditions those prescribed strategies by the mediator indeed would be played by the players? So these are some conditions, okay? So very standard condition. So there is something called max min value for any player. So call it Vi is nothing but the max min value defined like this. So it's nothing but, so I am playing, so it's me, right? So max over my strategies and min over all other strategies, okay? What is the worst that can happen, worst utility that I can pursue using the strategy profiles of other players, right? Then when it comes to me, I can take the best strategy that leads to more efficient outcome, right? So that's what it is. Min over the profiles of all the other players and max over my own strategy profiles, okay? So this is called max min. And so you fix all the strategies of all the other players, yes, n minus I. This is nothing but the set of all strategies except the ith player. So you fix it and you loop over all possible strategies of ith player, right? And take max over this, min over this. This is the minimum guaranteed payoff that the ith player can expect and hope for, right? So by notation, I mean, call this as like Vi. Okay, so now we introduce a condition called individual rationality. So a correlated strategy, alpha. So, I mean, by definition, correlated strategies are defined over subsets. So that subset can be the entire grand coalition consisting of all the players, right? So now a correlated strategy alpha, which is like a probability distribution over the pure strategy profiles of all the players, right? In the set N, is said to be individually rational if the utility to the ith player as per this correlated strategy is at least this max min payoff, right? So if this happens, right? So this is nothing but, I mean, the strategy prescribed by the mediator. This is the correlated strategy, right? So mediator takes the correlated strategy and randomly picks some pure strategy as per that correlated strategy distribution and prescribes to the players. And if this condition is satisfied, all the players naturally or voluntarily go ahead and execute the same strategy prescribed by the mediator. Fine? Very, very natural condition. Okay. So in general, you can think of this thing. So mediator prescribes a particular strategy SI to ith player, but ith player is not informed about the strategies of the other players. So ith player is only aware of his own strategy SI as prescribed by the mediator. Being a ith player, I don't know about all other player strategies. S minus I is nothing but profile of all strategies except ith player. So I'm not informed by the mediator about S minus I, which is like fair thing, right? So, right now, so define a function called delta I, which is like, so mediator prescribed SI to me, I can either play SI or I can choose my own other strategy as per my utility function, right? So it leads to definition of naturally defining a function delta I from my own set SI to SI, right? So mediator gives me one pure strategy profile. Either I can play the same thing or I can choose my own pure strategy according to my utility function. So this delta I defines a mapping from SI to SI for every player I. Now we define the important notion called correlated equilibrium. So we have seen Nash equilibrium, right? when all the players independently play the game without any cooperation. Now we are getting into, we are bringing in the notion of cooperation into the context of non-cooperative games through this correlated equilibria. So now, similar to Nash equilibrium, we should also have correlated equilibria. In spirit, it's the same definition, similar definition only. So now, given a finite strategic form game, NSI-UI, it's a three-tuple thing, right? This you must be like familiar by now. So a correlated strategy alpha, which is like a probability distribution over all possible pure strategies of all the players, recommended by a mediator, is called correlated equilibrium if for all possible functions delta I, which maps ith player's strategy set SI to the SI, so players can either choose the strategy prescribed by the mediator or something else. For that reason, this delta is coming. So the utility to the ith player as per the correlated strategy alpha, UI of alpha, should be at least this quantity. So I think you have seen this in the first talk perhaps actually. So this is nothing but, so if alpha is the probability distribution over all possible strategy profiles, yes. So this is like the corresponding probability, and UI of, so S minus I, and it can be SI, so, but we have this function delta I, right? Delta I of SI. That is the mapping that ith player uses to either to select his own strategy or the strategy prescribed by the mediator. Clear? This is a pure strategy. This is the pure strategies of all the other players. Together defines a strategy profile of all the players, using which you can look at the utility of the ith player. And this particular profile is played with a probability alpha of SI, S minus I, as per this correlated strategy equilibrium. It's a probability distribution all certain and right. So we use all those probabilities here. So this is the expected utility that any player can get by using his own mapping delta I. And this is the utility that ith player gets by using the strategy alpha I as prescribed by the mediator. So the utility due to the mediator prescribed strategy should be at least, right? This expected utility I can attain by using my own mapping function delta. Yeah. So I think these things are defined on general utility functions actually. So all possible utility functions should, for all possible forms, it should go through. There is no such, there are some conditions like they are like finite, compact, and these kind of conditions, but otherwise, form-wise, there is no specific restriction. And yeah, so you take the correlated strategy, which is nothing but a probability distribution over the strategy profiles, right? As per that distribution, he randomly picks one such profile. Profile meaning that strategy, it consists of strategies for all the players, and then prescribes, oh, okay, this is your strategy, this is your strategy, like that. Yes. So now, if you see the dynamics, how this game is being played versus the pure strategy game, in the non-cooperative games, wherein it's completely like non-cooperative, there is no mediator, no cooperation, players choose their best response strategies in any given situation. Now we are moving from completely non-cooperative scenario to cooperative scenario. In the context of cooperative scenario, agents themselves cooperate without the presence of any intermediary or mediator. So now between these two ends, the midpoint is this kind of things. So players are still non-cooperative, but there is a presence of a central authority kind of setting in the form of mediator and things like that. And mediators prescribe something, but again, having said that, there is no binding agreement or agreements between the mediator and the players. So he just tells something, players may or may not follow. Towards that direction, we are imposing all these things. There are no binding agreements. So this is the probability of this profile, right? As per, this is like a probability distribution. So for this profile, what is the probability? Yeah, the same alpha, right? So it's the same alpha, right? But the only difference is you assume all the other players follow the prescription of the mediator. I don't follow. I use my own delta I. I mean, delta is like any general function. It includes the scenario wherein I follow the mediator also. So now that comes, okay, that's a very good point. So he chooses, we are bringing in mediator in order to improve the social welfare of the players. Social welfare meaning that is the whole motivation in the beginning I told, right? So if players play independently, they choose one strategy. On the other hand, assume that there exists some kind of cooperation in some form. So God gives you that, let's say. Then in that case, 2-2 is the ideal profile one can hope for from the societal point of view. So what is societal thing? So welfare of everybody, right? So now how do you define welfare of everybody? There are many such forms. So one such form is maybe sum of utilities of all the players. So here in this case, it is 1 + 1, 2. Here in this case, 2 + 2, 4. So which is better than 2, right? So yeah, so we are going in, we'll exactly, I think you asked the right question, which made my life easier for the next slide actually. So how do you find such correlated strategies is the next question actually. So we form a simple linear program involving all these conditions, and the objective function of linear program is exactly this, whatever you asked. So that sum of utilities defines the social welfare. We choose that correlated strategy as like correlated strategy equilibrium, which maximizes the social welfare. So you apply that in this context, keep this table at the back of your mind actually. So 2 + 2 is higher than 1 + 1. Yeah. Exactly, that's where the tussle comes. That's where the tussle comes, and that's where we define this individual rationality. So in that process, so why would players follow the prescription given by the mediator, right? So they follow provided the utility that player gets through the correlated strategy by means of the recommendation by the mediator is at least this VI. Then it is like in the best interest of players to follow the recommendations by the mediator. So we use all these conditions in the next slide, so the linear program. So we looked at the definition of correlated equilibrium. Yeah. Yeah. Players tend to do that. But beyond that, there can be several good profiles. So it's like this, right? So suppose this is that 1, 1 thing, okay? Right? So you suggest something which is like 2, 2, which is better than this, which is fine, but still there could be some other profile which can give you more than that. So this is like minimum thing can happen. Beyond that, the gains can be like more than the VI, which is 1. So if gain that UI of alpha is it should be at least, so this 2 and 6 should be at least 1. Then it is in the best interest of the players to follow the suggestion or recommendation given by the mediator. So now mediator chooses that strategy profile, which is like socially efficient. That's where the objective function comes. So now how to find such a correlated equilibrium? That is the next question, right? So this is the sum of utilities. Yeah. 1 second. Recommended a pure strategy SI. No, they don't know, but they know the matrix, right? The original matrix they know. See, what exactly I am recommending to him and what exactly I am recommending to him, that you don't know. So what you know is what I am recommending to you. But everybody knows the matrix. That is common knowledge. See, that's the reason I am taking sum over all possible things. So I'm not relying on exactly what I prescribe to him and him. So in your calculation, so the common knowledge is the payoff matrix. So you know the payoff matrix and he knows the payoff matrix. But what you know at this point of time is, I recommended you, let's say X1, I recommend him Y2. You don't know that I recommended Y2 to him. All that you know is I recommended X1 to you. So now using X1 and using the payoff matrix, which is common knowledge to all the players, you can do these calculations. So this expression doesn't assume anything, the fact that what I'm being mediator, what I'm recommending to the other players, right? If you know that, so, I mean, these things are not required anyway. Okay, so now, you understood what is a correlated equilibrium, right? Now how to compute it? That's the next immediate question, computation of correlated equilibria. So I think that also we had a good discussion. So players, every player perceives a utility ui of alpha, if alpha is the correlated equilibrium. And for the mediator, since we are, the mediator looks at the social welfare, he takes sum of utilities of all the players. So that quantity, mediator wants to maximize. So now subject to the constraint. So this constraint, okay, is just a reformulation of the same condition. So if you see carefully, so it's nothing more than that. So this, if I use Si versus Si prime, so this Si prime comes from that delta I, that function. So the difference between these utilities should be greater than 0. Okay. This is the utility player gets using the correlated strategy, and this is the utility players get using this. So you pull these two things here that and adjust terms, you get that condition. And these two are the standard probability distribution based conditions. Okay. This is the simple linear program which gives you the correlated equilibrium, which maximizes the social welfare. In this case, we define social welfare to be sum of utilities of all the players. Clear? Okay, so what is the time? Okay, so this concludes this notion of correlated equilibria. So now you understood, right? So maybe I'll put this figure, which will be very useful. So this is like complete non-cooperation, non-cooperative games. So this end of the spectrum is cooperative games. Okay, so in the middle, we have all these things. So correlated equilibria. So in this case, we assume the presence of a mediator. Mediator and without any binding agreements. Right? So now we will look at another solution concept which is like intermediate to these two extremes, is called Nash bargaining solution. So we will now look at this Nash bargaining solution. So in following Nash bargaining solution, what we want to do is, we don't assume any presence of any intermediate authority. Sir, I couldn't hear you properly.
Is it something intrinsic to the structure of the game, or this is about the strategy that players take? So where we land on the spectrum of cooperativity,
okay.
Is this something intrinsic to the structure of the game, or it's depending on the strategies that the player?
Yeah, of course. We are talking about the structure of the game actually. So in the non-cooperative games, in the structure of the game, there is no intermediate person, and agents don't cooperate. They are like individuals. Being individual, my aim is always to maximize my payoff by playing the right strategy. So here, players, by definition, the structure of the game allows cooperation among the players, right? And accordingly, we will get into this and look at how to represent cooperative games and some solution concepts I mentioned in the agenda, right? Core and the Shapley value. At the end, the last half an hour, we'll get into that. And in between, we have this kind of correlated equilibria and Nash bargaining solution. So in correlated equilibria, the structure of the game allows presence of a third person, so called in mediator. but there are no binding agreements between mediator and the players. Okay? And now we will get into this next notion called Nash Bargaining solution. So here, as you rightly told, the structure of the game changes. So here we extend the structure of non-cooperative games, but we don't allow any intermediate person. But they're in the middle. So which means that some kind of cooperation should be there, right? So somewhere something has to change. So here we change the structure of the game by extending the possible feasible space. So how we will see that? Okay, so that's what exactly mentioned here. So according to Nash, cooperative actions can be seen as a culmination of bargaining process among the players. So in order to allow, additionally, there's something called bargaining to promote cooperation among the players. We extend the solution space. Okay, so solution is, we have that 1, 1, 2, 2, all these are like final solution points, right? We extend the solution space. Okay? So the strategy sets of players are extended to include additional strategies that capture bargaining. So we define the structure of such games with the help of a set of axioms. We will look into those things. So consider two-player bargaining problem. Okay, we will define its structure and everything clearly. So a bargaining problem is a two-tuple f comma d. F is a subset of R2, is a set of all feasible allocations, and D belongs to F, denotes disagreement outcome. So you can think of something like this, right? So your F can be something like this. This is your F. So, and let's say this can be your disagreement point. Okay, and by definition, so F is like convex and compact set, all these standard things we assume actually. So F is like convex and compact, and there exists some element V belongs to F such that V should be greater than the disagreement point. So in this case, you can easily see that. So any point here, all these points qualify to be V's, right? But if F is very small set, we assume that F should contain a point V such that V is strictly greater than D. So by definition, we are talking about a two-player thing. So every V and D are like two-dimensional things. When we say V greater than D, so by definition, V1 greater than D1, V2 greater than D2. That's what we are meaning, right? So let script B denotes the set of all possible bargaining problems. Now a bargaining solution is a function F, right? Which is like a mapping from the script B to F. So any bargaining problem instance that you consider, which consists of a two-tuple F comma D. So bargaining solution is a mapping from the two-tuple to some element in F. Okay. So now how to achieve and how to identify that element in F is nothing but the bargaining, Nash bargaining solution and the framework. We'll provide a solution to that. Okay. And we want this function F, bargaining solution, to satisfy some reasonable axioms. Okay. So here are the axioms. So very simple. I will not get into the this equation, but I will explain what it is, and very intuitive also. So the first axiom is strong efficiency. So you call an allocation x1 comma x2 belonging to F is strongly efficient. So this is your set F, right? So consider one point x1 here and another point 2 here. So now we say that x2 is strongly efficient than x1 provided. So x1 is a combination of 2 points, right? x11, x12. And similarly, x2 is a combination of 2 points, x21, x22. So we say that x2 is strongly efficient than x1 provided this component is strict greater than this and this component is strict greater than that. Component wise, it's better off. And second axiom is individual rationality. So that's what we told in the beginning. So the axiom states that the final solution, this your function, bargaining function F, right? So this function, so any bargaining problem instance is a two-tuple. So this function maps any bargaining problem instance to some element in F. So the final solution that we select should be at least D. then individual rationality satisfies. So in the correlated strategy equilibrium also we thought about the same thing, right? So mediator prescribes some strategies to all the players, and the players play those strategies provided it's very similar to this condition. So players follow the prescription of the mediators provided the utility perceived by the player as per the correlated strategy is at least this max min value. Same thing here. So the max min value Vi is captured here using this disagreement point D. If players don't follow the prescriptions, they end up playing their best strategies, which is nothing but that max min value, right? That is nothing but D in this context. So the final solution that is selected by the bargaining instance, that function f, should be at least D. D being the disagreement point. Very, very intuitive axiom. And this is called individual rationality. And the third axiom is scale invariance. So, I mean, this is nothing special about it. You linearly transform this set F to some other space. The same solution should hold, actually. So, linear transformations doesn't change the structure of the problem. So, that's what is the scale invariance. And the next axiom is independent of irrelevant alternatives. It's a very good one. What you do is, suppose this is your F, okay? And this being your disagreement point, right? Now, so your bargaining solution, which is this small function F, right? This is the bargaining problem instance. This is the bargaining solution. So this selects some point X belonging to F. Suppose if that X is here, right? Now you consider one subset G, subset of F, right? Suppose this is G, and this entire thing is your F. So G is subset of F. Now if this X is a solution to the full problem instance F comma D, and if that X falls in this set G, then, so we also have G comma D, another bargaining problem instance. So now, bargaining solution should select the same X. Why? Because, I mean, something like you can think of at the back of your mind, max over the bigger set. So if that belongs to one set here, which is like G subset of the big one, so this X continues to be max element in the same set, right? Something similar to that. So, which means that all the entries here are irrelevant, independent of irrelevant alternatives. That's what is the axiom. And intuitively very easy to imagine, right? And the last one is symmetry. So, labeling of players doesn't matter. So, that's what it is. So, if the positions of players 1 and 2 are completely symmetric, the solution should also treat them symmetrically. So, relabeling of the players doesn't change the solution. Okay, that's called symmetry. So now you have seen all these axioms, right? Strong efficiency, individual rationality, scale covariance, linear transformation doesn't change the solution, independent of irrelevant alternatives, and finally symmetry. So now based on all these 5 axioms, they define, I mean, Nash defined a solution concept like this. So, I mean, we kept on telling, right? F is the bargaining solution for the bargaining problem instance F and D. So it selects a point, it has to select a point X. So how to select that X? X is a combination of X1 comma X2, right? So how to select this X1 comma X2? That is done by this. So argmax, so you look at all possible elements in the set F, look at the product of X1 minus D1 and X2 minus D2. So which point X1 comma X2 maximizes this product, that is the solution. So Nash bargaining solution theorem says that for any 2-person bargaining problem instance F comma D, there exists a unique solution function that satisfies axioms 1 to 5, all these 5 axioms. And the solution function satisfies for any 2-person bargaining problem this. So any point that maximizes this satisfies all these axioms. That is a final takeaway. And in this process, you are trying to attain, trying to reach those points. So D is the mini-max kind of point based on the utilities of all the players. So this corresponds to the Nash equilibrium outcomes. So now we are going beyond Nash equilibrium, Nash equilibrium sort of outcomes leading to cooperation among the agents. So there is no intermediate player and there is no explicit cooperation among the players, but we are trying to achieve better outcomes by extending the strategy space of the players. So we are looking at all possible ways to bring in cooperation, right? So far we have seen, our journey from non-cooperative to cooperative. So we looked at a correlated strategies where we saw the presence of intermediate person. In that context, we looked at correlated equilibria. And the next possible alternative to bring in cooperation into the setting of the players is through Nash bargaining solution. So wherein there is no presence, the intermediate authority or central authority is not present. However, we extend the strategies of all the players and thereby we try to achieve cooperation. This is like another style of bringing in cooperation into the framework. And the third thing is explicit cooperation. Players directly get into coalitions and form teams and so on and so forth. That we will see immediately now. Not necessary. Why? We never assumed bargaining power of all the players are same. So that's the reason we try to maximize this. So if, as you rightly told, if the bargaining power of one person is, let's say player one is high, so then, so this is the player one's utility, and this is player two's utility. So if bargaining power of player one is high, then, so we should select a point X which is like, which belongs to this space. Right? In this side. So now if bargaining power of player one is high, maybe we tend to choose some point towards this side. If bargaining power of player two is high, then we may tend to choose some point towards this direction actually. But any of those points satisfy those things. So any point belonging to this region satisfies all five axioms. So that's the reason this theorem doesn't assume anything on the bargaining power of the players. It is up to the players. Okay? So far it's clear. Now I'm getting into the third part, cooperative games, wherein players explicitly form teams. And we should allow our utility functions should consider subsets of the players and we attach utilities to the subset of players. This is like direct, so saying that, oh, okay, so can we form a team, let's play together. It's like that actually, right? So towards that direction, so we need to develop the necessary mathematical framework. It's called transferable utility games, TU games. So TU game is defined as like a two tuple, n comma v. N is the set of players, of course, and v is a set function defined on all possible subsets 2 to the power of n to real numbers. So in other words, v is a function, set function, which attaches a real number for every possible subset of the players. So that real value is nothing but the utility that this subset of players can together achieve, or that subset of players can together achieve. So whatever may be the subset of the players, we will attach a real number representing the utility that can be jointly achieved by the players in that subset. Okay? So, okay. So now VC represents, so for any correlation C, which is like subset of N, is called the worth of the correlation or the payoff together the players in the correlation C can achieve. So you can give any type of interpretation. So now, so finally, so what is the biggest problem in cooperative games? So we have so subsets 1, C1, C2, C3, etc. C2 to the power of N. All possible subsets, we have real numbers, right? Some real number 1, 2, 3, etc. Some number as per that V function actually. So now the major problem in cooperative game theory is these are all like given. This is a problem instance actually, N comma V. So now the output is so this is called payoff vector. So all these correlations are fine, that is good. But end of the day, whether it is like cooperative game or non-cooperative game, it doesn't matter. Finally, what we should do, we should derive the payoffs to the players, given a problem instance. That is the ultimate goal. So that is called payoff vector. So it's like n tuple, x1, x2, etc., xn. So from this type of input, so how to derive a payoff vector like this? This is the main problem handled in cooperative games here. So towards this direction, they define something called solution concepts. So every solution, the goal of every solution concept is, given a problem instance like this, how to attach a payoff vector to that problem instance. Okay? So they might, some solution concepts attach a single and unique payoff vector. So some solution concepts derive multiple types of payoff vectors depending on their format, structure, underlying algorithm, right? So there are, so this mapping is done through solution concepts. So examples of solution concepts are called core, Shapley value. There are like different, you can think of algorithms or solution concepts which achieve this objective actually, this input to that output. Clear? Okay, so before getting into some details of core and Shapley value, we'll just see and digest what this form means and some examples, nothing more than that, okay? So consider one example of this format n comma v. So this example is called divide the dollar, majority voting game. So consider there are like, there is $300 which needs to be divided between 3 players, okay? And the players get 0 payoff unless there is some pair of players 1, 2, or 2, 3, or 1, 3 who propose the same allocation. So what does this mean? In which case they get this allocation? So either 1, 2, so 1, 2, the set 1, 2, or 2, 3, or 1, 3. Any one pair should propose the same allocation, then players get that allocation. Otherwise, every player will get 0 actually. So if 1, 2, and 2, 3, and 1, 3 propose some allocation, then they get 300. Otherwise, they don't get anything. And together, the total amount available is $300, right? That $300 should be equally divided among all the 3 players. So how much amount I get is equal to my payoff, how much amount you get is equal to your payoff, and how much amount you get as a third player is your payoff. But together, all of us can, what is our total gain? It's obviously 300, right? Because available amount is 300, right? So value of 1, 2, 3, this is called grand correlation because all 3 players are involved. Value of grand correlation is of course 300. And the value of any subset of players containing 2 players is also 300 because of this rule actually. This is the rule of the game. We defined the game in such a way that if this subset defines one allocation, which is, so I propose, so I am player 1, if I propose 150, 0, this is player 1, and player 2 also proposes 150, 0, that's it. So this is the final outcome as per the rule. On the other hand, if player 1 proposes 150, 0, and player 2 proposes, let's say 0, 150, and 150, they are not matching. So then 1 and 2 don't get anything as per the rule of the game. So players get 0 payoff unless there is some pair of players 1, 2, or 2, 3, or 1, 3 who propose the same allocation. Allocation should be the same. So now accordingly you can write down like this. So in being individual player, I will get 0 because the rule says that 2 players payoffs should be the same. Okay, this is the structure of the game. Okay, so now, yeah, we are getting into this solution concept. So let's start with core. So how the solution concept core derives a payoff vector x1, x2, etc., xn given a cooperative game instance in the form of this tuple n comma v, where n is the set of players, v is a set function. Right? So it attaches like this. So a payoff vector x is in the core right? If of that TU game, transferable utility game, n comma v, if and only if, for all possible subsets C, right? So we are saying that core derives a payoff vector x1 to etc. xn. We say that this element is in core if you take any subset of the players, right? C subset of n. So C consists of for all players I belonging to C. So as per this payoff vector, how much they are getting? Right? Sum over xi's I belong to C. That is the total payoff all the players in the set C will get as per this payoff vector. If this value is greater than or equal to V of C, from where you get V of C's? This is the input, right? That's given in the input. Input is n comma v, v is a set function actually. So that's part of the input. So input is given and you are supposed to derive a payoff vector x1, x2, etc. xn. We say that a payoff vector belongs to the set called core if for every possible subset C of n, it should hold actually. So sum over all xi's I belong to C should be at least V of C. V of C is part of the input. And for all possible subsets, if this condition is true, then we say that this vector belongs to core. So this is also called correlational rationality. I mean, there's another name to this. So every correlation C, as per that set function V, they derive a value V of C. But now, as per our solution concept, we say that x1, x2, etc. xn is the final solution, which satisfies this condition wherein all the players in C, following this solution concept core, they get jointly they get a utility which is at least V of C. This is called correlational rationality. That can happen. Yeah, but depending on the structure of the problem, if the underlying, okay, it's a very good point. If the set function V satisfies some properties like supermodularity and things like that, we promote bigger correlations. Very good point. If that is not the case, smaller correlations will form. Absolutely. Okay. Okay, so there are like some properties. So what is the first property? So core is nothing but a set of all such payoff allocations, right? So now is core always non-empty? So answer is no, core can be empty. So one example is this. So consider that voting game we have seen, right? This game. We slightly change this rule and accordingly the core will be empty. That's what is shown here. So consider that majority voting divide game. I mean, here it is called majority voting because there are 3 players. If at least 2 players propose the same allocation, we follow that. Meaning that if majority players propose the same allocation, we follow it, right? That's the reason it's called majority voting game. Majority divide the dollar game actually. So we slightly make a change to that in the rule of the game in the following sense. If any player I is offered a positive payoff, the other 2 players must get less than 300, which is the value of their correlation. Regardless of the final allocation, there is a correlation that could gain if we can get an opportunity. Okay, so now the question is the core always non-empty? No, core can be empty in the following setting. Suppose you 149.5. So 0.5 you take out and give it to the first player, right? So now if this is the allocation proposed by player 2 and 3 jointly, right? This will not be part of core because so player 1 can form a correlation with either player 2 or player 3 in such a way that he says that, okay, I will propose 1 minus epsilon. Suppose if he forms a team with this, So 149.5 plus epsilon and 149.5. So this is so if any player I is offered a positive payoff, the other two players must get less than 300, which is the value of their correlation. Regardless of the final allocation, there is a correlation that would gain if they can get an opportunity to negotiate effectively against this allocation. Okay. So if this is the allocation, so then what players 2 and 3 can jointly do? They can jointly propose an allocation which is like 149.5 plus epsilon, 149.5 plus epsilon, and 1 minus 2 epsilon, where epsilon is like very, very small quantity. So if both players, these two players can jointly propose this, right? This is like, beneficial solution than this. Now again, so, follow this argument. Another next epsilon would be there. So there is no end to that, right? Initial payoff vector. So that's what we have shown here. So in the divide dollar game, initial V is this. Okay. So, we are trying to create an instance wherein core is empty. So core need not exist for all the games. That's the main message here. Nothing so serious. You can always cook up your own favorite example. And another property is core always unique? So answer is no. Core need not be unique. So in some cases it may be, but in some cases it can contain more than one element. So, and core can be empty, countable, or even it may have uncountable set actually. So all possibilities can exist. Okay. Now we will get into the another second solution concept, Shapley value. So the goal of, again, this solution concept is also same thing. So given this instance, how to derive a payoff vector. So so far we have seen core. So in case of core, as we mentioned here, so core can be empty, or it can be a finite set, or it can be even uncountable set actually. So all possibilities exist. So now somebody can stand up and ask, can I design an algorithm given this input to derive this output, which can give unique outcome for any given instance, input instance, cooperative game input instance. So that's what is achieved by Shapley value. So Shapley value, given any cooperative game instance, it derives a single vector. So how it derives, we will see actually. So again, it is based on some solution, some axioms. So we will just briefly look at those axioms. This is the simple standard notation, right? Given a game, cooperative game n comma v, we denote the Shapley value to be phi of n comma v. N comma v is the input instance, phi is the mapping. So finally it derives phi 1 of nv, phi 2 of nv, etc., phi n of nv. The same I wrote like x1, x2, etc., xn. So x1 is same as phi 1 of nv, right? It's a payoff vector. So where phi I of nv is the expected payoff to the player I. Fine. Now, this solution concept is also based on a set of axioms. So the first axiom is symmetry, the standard thing. Relabeling of the player should not change the underlying structure of the game, which is like very standard axiom. So it's called symmetry. And the second one axiom is called linearity. So again, it's a very standard thing in mathematics. So I think most of you have math background, right? So I don't need to worry much. So consider two cooperative game instances, n comma v and n comma w, on the same set of players n, right? Two relational games. And you consider any p, which is like in between 0 and 1. Take this linear combination, right? So on the same set n, consider the linear combination game pv plus 1 minus p of w. Now, Shapley value of this game, which is like a linear combination of these two games v and w, is nothing but so p multiplied by Shapley value of ith player in the game v plus 1 minus p multiplied by Shapley value of ith player in the game w. This is called linear, very, very standard axiom. And third one is carrier axiom. So what it says is, suppose you consider, just to give you the intuition of what carrier axiom means. So consider there are n players. So out of n players, only some subset of them are really useful in terms of deriving value to that entire grand correlation, whereas some other subset of players are like dummy. Dummy in the sense their presence in the system is no use to the system actually. Whether they are present or not present doesn't matter. They are called dummy players. Now the value of the entire system is nothing but the value of these people who actually work. The presence of dummy players doesn't matter, right? That's what it is. So then in the solution, final solution that you derive, right? In that payoff vector also, for all the players which are like dummy, they should get 0 payoff, right? Which is like intuitively correct. Because the value of the entire set is same as the value of the set subset wherein players who actually work are part of, then the final solution should attach a payoff 0 to all the dummy players. So this kind of notion is captured using this carrier axiom. So now how to define the dummy players, right? So you consider the correlational game instance n comma v. Now for all possible subsets C, right? The value of that set C is nothing but it's nothing but C intersection D. So if that set C consists of some dummy players, so their value is nothing. They don't add any value to the system, right? So you just look at C intersection D. So V of C intersection D is equal to V of D. D is nothing but the set of players who actually work towards generating value. So for all possible subsets, if this happens, then D is called carrier of that cooperative game n comma v. And in that case, what happens is the final solution concept phi, our Shapley value solution concept phi, right? It attaches a value I phi I to the ith player. So sum of the allocations of all the players belonging to that carrier should be the value of the entire grand correlation. So dummy players should get 0. Okay, clear? So now these three axioms are there. Symmetry, relabeling of players should not change the structure of the game. Linearity, which is like, again, standard definition. And carrier axiom, which defines so-called useful players and not so useful players. So now based on these three axioms, Shapley defined, by the way, for his seminal work, he got Nobel Prize in 2000s. I don't remember exactly which it is. And this work is done around 1952 or 53. So after roughly 50 years of his work, he got Nobel Prize. So given a correlational game n comma v, there is a unique payoff allocation, x, the payoff vector x, which is same as the phi function, Shapley value function, that divides the full payoff of the grand correlation, and that satisfies these three properties: symmetry, linearity, and carrier axioms. So this is like a theorem. It has a formal proof and etc. We don't get into that. And the beauty is, as I already mentioned, this derives a single payoff vector as opposed to core, wherein core can be empty or non-empty, finite or uncountable set, etc. All possibilities exist. But as opposed to that, so Shapley value always derives a single payoff vector for any instance of the cooperative game. Now we will see what is the structure to that, how to derive that. So here is the closed form expression to derive the Shapley value payoffs for every player. So x1, x2, etc. xn. So xi is nothing but phi I in our notation here. So given a correlational game n comma v, the Shapley value of ith player is defined by this. So here, if you see the equation, don't worry. So it's nothing but you look at marginal payoffs. So you consider a subset C, which consists of ith player, right? So consider a subset C. So player I is belonging to C. Okay, I think as per that, so player I doesn't belong to C, right? So I is not part of C. Now you look at value of C union I minus V of C only. So ith player is not part of the set C, then the value of that set is V of C. Now ith player because you are interested in computing the ith player Shapley value, right? So you add ith player to that set C, C union I. What is the value of that? So look at the difference between these two values. This is called marginal contribution of the ith player to the set C. Okay? So how many ways I can form the set C if there are n players? So how many ways I can form the set C? These many ways. So these are the number of ways I can construct a C, and a given C, this is called the marginal value that ith player derives, right, with respect to the set C. Now you have to take sum over all possible C's. So this equation is with respect to a particular C. Now you should take all possible C's, right? C's are nothing but subsets. Subsets over, n minus I. So I'm worrying about ith player, right? So ith player should not be part of the set C. So you remove I from the system, you are left with n minus I. Look at all possible subsets of n minus I, namely C's, and you fix a particular C. This is the expected payoff because of this probability thing. This is called the expected marginal payoff that ith player adds value to the subset C. So very simple and cute interpretation to this. And this is like a fixed number. For every player, you get a single number. So hence it's a unique solution. Okay, so the same thing is explained here. So for the same, this game, the $300, so based on the majority prescription, so we have to divide, right? So following that, every player should get 100, 100, 100, because majority can be formed by using players 1, 2, or 2, 3, or 1, 3. So all players are equal in terms of the power, based on your question. No single player has additional power. So by the way, in order to bring in the power concept into the framework, I don't know whether I have those examples. I don't have those examples. You can change this definition. So what we can change is the same game you consider, and the rule of the game is defined as I choose that payoff vector which is suggested by 1 and 2 together. Then I'm forgetting about 3. So following our carrier axiom, 3 is what? Dummy player. So what is D? D consists of only 1 and 2. Out of our 3 players, D will be 1 and 2. So now Shapley value should be how much? So Shapley value will be 1 and 2 players, right? 150, 150, 0. So you keep changing all these numbers. If you say that 2, 3, so accordingly 0 will be here, like that. 1 player will be dummy. So any questions? Okay, so I reached the end of the presentation. So far, it's clear, right? So, I know that it's a very short presentation, but I want to convey the message in a meaningful manner. So I tried my best to convey this using at least kind of pictorial thing. So the summary of my presentation is, so we have non-cooperative games at one end of the spectrum and cooperative games the other end. So what is the use of cooperative games? Eventually, players' individual payoff should be improved, and in a sense, the overall societal benefit, so-called the social welfare, we measure social welfare as sum of utilities, that thing should be improved. And we should provide mechanisms which can realize these kind of enhanced societal benefits, and in that process, individual benefits also, because we can't enforce, right? All said and done, these agents are like autonomous and individual. We cannot dictate and we cannot enforce them to take a particular strategy. So we should have, the necessary framework which allows these autonomous and individual agents voluntarily choose those strategies which lead to better outcomes in terms of which leads to cooperation among themselves. So in that there are multiple structures. One is correlated equilibria, which has mediators, presence of mediators, and another form is Nash Bargaining solution, wherein you expand the strategy space of the players. So here we don't expand the strategy space of the players. So here we expand the strategy space of the players. And the last one is we change the structure of the game by bringing in coalitions of the players who can like form teams and then cooperate, right? And to represent that, we have this separate n comma v tuple, which is like different from the non-cooperative game has 3 tuple, right? N, S, I, U, I. So this is the non-cooperative game structure. So we departed from that and moved to another formulation called n comma v, n is set of players, v is a set function. So which enables individuals to form teams, and in that context the basic problem would be, so given a function which attaches a value to all possible correlations, how to derive a payoff vector. That is the primary problem in cooperative games. Towards that, several solution concepts are defined. So we looked at 2 examples, core and Shapley value. So in case of core, it need not be unique, and sometimes it can be empty, and sometimes it can be derive like more than one solution. So suppose if you have more than one solution, so I think even in cooperative, non-cooperative games, equilibria can be more than one. So then one natural problem is which one to choose. So the very first slide I started off with, right? So it has a single equilibrium, 1 and 1. If players are like allowed to play as per their wish, so they end up playing 1 comma 1, y1, y2 strategy profile. Suppose if there is like more than one Nash equilibrium, how players coordinate among themselves to land into a particular outcome, right? So we don't know. So that kind of issue also comes here. If there is like more than one point in the core, which one to select actually? So perhaps we have to deploy, further set of rules or whatever, some fairness criteria, which helps to pick one element out of these many elements. So in order to avoid those issues, Shapley value is another solution concept. So by the way, all these things are based on certain axioms, right? So this is also based on a set of axioms, and it derives a single outcome. So wherein we don't have all these problems of like, if there are multiple solutions, which one to select? That problem will not arise. So, by the way, since I have some more time, I just want to highlight that this is like very, very important problem. This is called prisoner's dilemma problem, actually. So here, in one-shot game, if players are asked to play this game only once, then both players select y1 and y2. So this is the outcome. And we looked at some structures wherein we can depart from this outcome and move towards 2 comma 2 outcome using these kind of constructs. But assume that you are here only. Right? But assume that this same game is played multiple times, repeatedly. This is called repeated games. So, there is a huge area called evolution of cooperation. So in our, human societies, right? Cooperation do exist. That's the reason we are all surviving. So even though inherently we may be rational and intelligent players, we also do cooperate. That social aspect and social angle do exist. So which means that our human societies are like cooperative. That's the reason we are like sustaining and living. So how to develop models, right, to explain this kind of cooperation? So this is called evolution of cooperation using game theoretic models. It's like very, very well studied area from last several decades. I would say at least some thousands of papers are written. Still it is active area. And most of these papers are based on a few game theoretic structures. One of them is called this prisoner's dilemma, this game format actually. So they say that if players are asked to play the game only once, a single round, then they end up playing this. Then later, they have done another game, another experiment wherein players are given the same payoff matrix, but they are asked to play multiple times. Then sometimes players started playing this strategy. So in one shot, for sure, they played only this. But if players are asked to play this game repeatedly, 10 times, 100 times, 1,000 times, in between, they ended up playing this strategy profile also. Then you can immediately ask, oh, what is happening? Why, only sometimes. They ended up playing this strategy only sometimes. Why is that? Can anyone tell? Suppose the repetition is going on, right? And in this particular round, both players played this strategy. Why in the next round, people ended up not playing that strategy, same strategy profile? x comma x1 comma x2. There is one more simple reasoning behind it. You look at payoff numbers. Absolutely, that's the reason. So they assume that in the next round, so I'm first player, you are the second player, I assume that you continue to play x2. So if I switch from x1 to y1, 2 to 6, my payoff is better off, right? So suppose if the other player continues to play x2, I'm really rational and selfish player, I move from x1 to y1, my payoff is improved. So that is seen by the second player in the next round, and he will become angry, right? So in the next second follow-up round, he will also play y2. So both ended up being here. Then after some rounds, they start again jumping back. So this is called tit for tat, all these things. So you punish me, I punish you. It's like that. There are multiple such, yeah. That is true, yeah. Follow exactly, yeah. That's right. The finiteness also should come into the argument. That I completely agree. But that is not the only thing. So along with that reasoning, with finiteness argument, together goes through. So that's the reason, yeah. So, I just wanted to tell, so this is like huge area. So if anybody wants to explore, you just try to search in Google. So evolution of cooperation in using social dilemmas. This particular example is called prisoner's dilemma. So what is dilemma? Nash equilibrium outcomes. Nash equilibrium gives lesser payoffs. But however, there exists some outcome which is not Nash equilibrium outcome, but payoffs are strictly better than Nash equilibrium outcome. So any game has this kind of structure is called social dilemma game. So they call it like social dilemmas. In particular, prisoner's dilemma is one example of social dilemmas. There are many such variants of social dilemma games. So I'm just giving you the keywords. So social dilemmas, evolution of cooperation, you get access to all those 1,000 papers. Okay, fine. So that's what I have for today. Thank you very much. So if you have any queries, so please feel free to send email to this email ID. So sorry, I couldn't put it there. Either this email ID or any one of these email IDs, you can drop an email to me. I'll definitely respond. Okay, fine. Thank you. If there are no further questions, we'll conclude.